Okay, let us start. Remember that we started with the topic of root locus, and today we are going to repeat these 4 rules that we have found so far, and we are going to try to draw different root loci in order to be able to grasp the topic in a better way. So remember, in general, we have a closed loop system that is composed of a forward path transfer function and a feedback path transfer function given like this. And here, the open loop transfer function is g of s, h of s. Okay? It is dependent on a single parameter k. All right? And I have a ratio of polynomials n of s divided by d of s here. That is the open loop transfer function, and root locus is trying to draw the closed loop properties, or trying to understand something about the closed loop given the open loop transfer function. Okay, we have a single parameter k. This k is going to change between 0 and it's going to go to infinity. So it is always going to be positive except when it is 0. And as this k changes, closed loop properties are going to change. And root locus is trying to obtain those closed loop properties when k changes between 0 and infinity. Remember that the closed loop transfer function is g of s divided by 1 plus g of s h of s. As a result, the closed loop poles, which are the important properties that we are after, closed loop poles would satisfy the equation 1 plus g of s h of s is equal to 0. And when I substitute this formula related to k into this one, and if I arrange the properties, I get the characteristic polynomial given as follows. Okay? So here we can either use this equation, or sometimes I can write this equation as g of s h of s is equal to minus 1. We can use this equation as any of these equations would be equivalent for us, and we're going to be trying to obtain the closed loop poles satisfying this equation, roots of the characteristic polynomial. This is our characteristic polynomial for the closed loop system. Okay. So remember, we have started with an example. In this example, we had a proportional controller k, and we had a 4th order system. In this case, I have s plus 1, plus 2, plus 3, and plus 4 here. This was my system, and we were required to draw the root locus. Okay? In this case, the first thing that we have to do is to look at the open loop transfer function. Open loop transfer function, in this case, is k times this long thing. Okay, so I have s plus 1, plus 3, and plus 4. Okay? This actually tells us that we have one open loop 0 at s equals to 0, and 4 open loop poles. Okay? We have at s equals to minus 1, minus 2, minus 3, and minus 4. In general, we are going to say that, in this case, for example, we have n is equal to 1 open loop zeros. Okay? And we have n that is equal to 4 open loop poles. Okay? And as soon as we have those quantities, I can actually put them into a complex plane and as a beginning of the root locus. There is one open loop 0 and 4 open loop poles, minus 3, minus 4. So here, remember when we try to draw the root locus, we generally try to derive some rules. And using the first four rules, we can draw almost any root locus. We can come up with a reasonable approximation. And the remaining two rules will be some details related to the root locus. And here, I can actually write this equation, 1 plus gh is equal to 0, or I can write d of s plus k n of s is equal to 0. D of s here is the denominator, and its degree is n, which is equal to 4. N of s is the numerator polynomial, and its degree is n is equal to 1. Okay? And when I write the characteristic polynomial, I get this one, s plus 1, s plus 2, 3, and 4 plus ks is equal to 0. It's a fourth order polynomial. And this is one of the rules actually. Okay? The number of branches or trajectories in the root locus is given as maximum of m and n. Okay? So there is an nth order polynomial, there is an mth order polynomial here, and the overall order of the characteristic polynomial is given as maximum of m and n. That might be a general rule. And in this case, since n is larger, then that means that in this case we have four trajectories. Okay? When I complete this root locus, that is going to be, I will draw the trajectories of four different closed loop poles. So this is rule 1. Rule 2 is start and end points. Okay? So start points means k is equal to 0. And remember how we actually reason about this. So here, one of the equations that we like is g of s h of s is equal to minus 1. This is my g of s h of s. So I see here, g of s h of s is equal to one equation can be written as this. Any s in the root locus should satisfy this equation for some positive or 0k value. Any s that would satisfy this equation for some positive or 0k value would be inside the root locus. I will draw them at that point onto the root locus. So here, for satisfying this equation, for k is equal to 0 is going to be the start point of the root locus. For k is equal to 0, for the right hand side to be equal to minus 1, this ratio should be infinite, so that I have 0 times infinity, any number, to satisfy this equation. Okay? So that actually means that at k is equal to 0, the root locus is going to make this ratio infinite, meaning that at k is equal to 0, root locus is going to be at open loop poles. Okay? And endpoints are the cases when k goes to infinity. If k is infinity, in order to be able to satisfy this equation, this ratio should be equal to 0. Because if this was a non-zero number, when k is equal to infinity, the right-hand side would be infinite. Okay? So to satisfy this equality, the ratio should be equal to 0 when k is infinity. So this ratio is 0 when s equals to 0. And s equals to 0 is one of the open loop zeros. So root locus ends either at open loop zeros or sometime else when this ratio is again equal to 0. We see that this ratio is equal to 0 at s equals to 0, but also it is 0 when s goes to infinity. Okay? So that is also when root locus ends. So either at open loop zeros or when s goes to infinity. Okay? In both cases, this ratio is equal to 0, meaning that this equation might be satisfied. So here I'm going to draw 4 trajectories, and I see that I have only one open loop zero. So we have one open loop pole, 4 open loop poles and one open loop zero. This is going to mean that among these 4 trajectories, starting from these open loop poles, only one of them is going to go to this open loop 0. The other three, they are going to go to infinity. They are going to get larger and larger, and they are going to go to infinity. When some poles go to infinity, they go on to the asymptotes. Okay, so this is going to be related to the concept of an asymptote. Okay, this is smiley here. Okay, so here, let us try to concentrate on the root locus on the real axis. That is the third rule, root locus on the real axis. In this case, we are going to consider which parts of the root locus on the real axis, which points on the real axis would be included into the root locus. Let us try to reason about this. Any s should satisfy this equation to be on the root locus. Suppose that my s is somewhere here on the real line. Okay? If my s is real and positive, I see that this is positive, positive, positive. All of these terms are positive when s is real and positive. Meaning that I will not be able to satisfy this equation for a positive or 0k when s is anywhere on this line. Okay? That actually means that this part of the real axis cannot be included in the root locus. On the other hand, what happens if s is somewhere here in this interval? If s is real and in this interval s is something like minus 0.5, for example, okay? In that case, this thing is negative and this thing is positive, positive, positive, positive. So we see that this ratio then would become a negative number if s is real and between minus 1 and 0. And in that case, by choosing a positive k, I will be able to satisfy this equation. That means that for any s in this interval, I'm going to be able to satisfy the root locus equation, meaning that any number in this interval on this part of the real axis will be included in the root locus. If I look at this interval here, then I have a number s between minus 1 and minus 2, a real number again. Okay? And if I substitute, for example, minus 1.5 there, this is negative, negative, and the rest becomes positive. Okay? And in that case, this negative and negative would make a positive number. So I have negative, negative, and three positive numbers. And the multiplication in general would make a positive number. And choosing k a positive, I will not be able to satisfy this equation. I will not be able to make the right-hand side minus 1 anymore. Okay, that means that this part of the real axis is not included either. On the other hand, if I look at this interval, s is something like minus 2.2, for example. Okay? In that case, this number would also become negative. Okay? So then I see that this ratio in the overall becomes a negative number, and by choosing a positive k value, I will be able to choose that k value to satisfy this equation. That means that this part of the real axis is also included. And if you continue with this logic, you're going to see that this part of the real axis will also be included, and the other parts will not be included. So what happens if we can talk about the complex poles. They won't cause any difficulty in this logic actually. But before that, I would like to write the general rule here for the root locus on the real axis. A point, so let us write here, a point on the real axis is included in the root locus if the number of open loop poles and zeros to its right is odd. Okay? This is the general rule for the root locus on the real axis. So for deciding whether a point on the real axis is in the root locus or not, I look at the total number of open loop poles and zeros to its right. Okay? And if that total number is is actually an odd number, then I would say that that part is included. So for an S point on this part of the real axis, what is the total number of open loop poles and zeros to the right? It is 0, and in that case it's an even number. So that means that this part is not included. What is that number here in this interval? The total number of open loop poles and zeros is 1. That actually means that it's an odd number. This interval is included. And when I look at the total number of poles and zeros in this interval to the right, it is 2, 1, 2, which is an even number, meaning that this interval is not included, this is included, etc. Okay, so that is our rule. So if I instead have these open loop poles and zeros, so let me say that, for example, I have 2 open loop poles here and the 1 open loop pole here, and let me say that there is a 0 here. Okay? So in this case, I will fill in the real axis as follows. I have real S, imaginary S here. So I will fill in. What about this interval? Do you think this is included? The number of total number of open loop poles and zeros to the right is not even. It's not odd. It's 0 in this case. And what about this interval? This is included because the total number is 1 to the right here. So when I come here to these imaginary open loop poles, these complex open loop poles, do you think they will change anything? So they won't affect anything because here we see that these 2 poles would correspond to a polynomial like this, s minus sigma squared plus omega squared. These 2 closed loop poles, these 2 open loop poles would always correspond to a polynomial like this. Okay? And when I evaluate such a polynomial at any real number, when I evaluate such a polynomial at any real number, I would always get a positive term. This is never going to be negative. Meaning that if I have such a term here in this ratio, it is never going to give me a negative number. Meaning that it is never going to be able to change the conclusions. So here, if I use this rule here, for any point here like this, the total number of open loop poles and zeros to the right is 3. And these 2 will never be able to change the evenness or oddness of that number. Okay? So you can either forget about these two poles when trying to find the real axis root locus, or you can count them as double poles like this, and so that they won't change anything. So do you think this part of the real axis is included or not in the root locus? What is the total number of open loop poles and zeros to the right? It's 3, it's an odd number, so we're going to be including that part as well. What about this interval in that case? This makes 4, which is an even number, so this part is not going to be included in the root locus at all. Okay? So here, as soon as you put the real axis parts of the root locus, you can put some arrows there. The arrows should get away from the open loop poles, and the arrows should go towards the open loop zeros. So here, I'm putting some arrows getting away from the open loop poles, and I'm putting arrows going towards the open loop zeros. Okay? So here, as soon as, and here I can actually do a similar thing. So here I have arrows getting away from the open loop poles and arrows going towards the open loop zeros. Okay? And as soon as you look at this picture, you might start understanding actually what is going to happen. We see that this pole, as we increase k from 0 to infinity, it's going to go towards this 0. And these 2 poles are going to approach each other for some time, and they're going to meet at a single point for some k. And afterwards, they're going to go to infinity by going complex. And then this pole is going to go towards the left and it's going to diverge away to infinity on that line. Okay? So here the fourth and the final rule that we are going to learn is related to the asymptotes here. The asymptotes is going to determine the behavior of the root locus when the magnitude of the closed loop poles would go to infinity. Okay? So here, in general, the total number of asymptotes is going to be n minus n. Okay? So let us say rule 4. Rule 4 is related to the asymptotes. Okay? So here, if the n is the number of open loop poles, and m is the number of open loop zeros, okay, the total number of asymptotes is n minus m. Okay? And in this case, this number for this example is 4, this number is 1, meaning that the number of asymptotes is going to be equal to 3. And remember that this equation has to be satisfied even when s goes to infinity. S going to infinity is characterizing our asymptotes, and we see that as s goes to infinity, this ratio is going to turn into k s to the 4. Okay? And similarly, this is going to be a k times 1 over s cubed. Okay? And here, if I look at the angle of both sides here, if I look at the angle of both sides, this is going to be minus 3, angle of this s is going to be plus minus 2k plus 1, 180 degrees. The angle of the point minus 1 can be represented like this, and the angle of 1 over s cubed, angle of k is always 0, and angle of 1 over s cubed is minus 3 angle of s. So here this 3 is nothing but n minus m here. Okay, it is 4 minus 1 in this case. And in the general case, we would have n minus m, angle of s is going to be equal to this number. Okay? So here we generally classify the asymptotes as the first with the angle of the first asymptote and the angle between the asymptotes. Angle of the first asymptote is given as 180 divided by n minus m. Okay? So here, this becomes here 60 degrees. Okay? For this example, it is 60 degrees. And the angle between asymptotes is given as twice this number, 360 divided by n minus m. So this gives me 120 degrees. And there is also something called as centroid, which is the intersection points of the asymptotes. In the last lecture, we derived these formulas, but we never derived the formula for the centroid at all. This is the intersection points of the asymptotes, and it is defined as the centroid of the asymptotes. This is given as summation of the open loop poles minus summation of the open loop zeros divided by n minus m. Okay, so this is the formula, and we never derived this in the classroom. So actually, I was deriving this when I was first giving 302. Ondan sonra hiç gerek yoktu falan dedi öğrenciler. Ondan sonra bir daha drive edemedim. İlk hoca olunca insan böyle sınıfta böyle her şeyi mutlaka anlatmalıyım. Onlar ne kadar istemeseler de bunu kafalarına sokmalıyım diye uğraşıyor ama her zaman bu iyi sonuçlar alamayamaz. Okay, so I no longer derive this in classroom, but if you like, I can share you with the proof. If you are really interested, I can share you the proof. So here let us try to look at this formula. Summation of the open loop poles. The open loop poles are at minus 1, minus 2, minus 3, and minus 4, and their summation is minus 10. minus summation of the open loop zeros. There is only one zero, which is 0, and that actually means that this is minus 10 divided by 3. Okay? So the intersection points of the asymptotes are given here at this point. And the asymptotes, the angle of the first asymptote with the positive real axis is going to be 60 degrees, meaning that my first asymptote is actually going to be looking like this. The second asymptote is going to be 120 degrees apart from or away from the first asymptote. The angle of this one is 60 degrees. So 120 degrees later, we are going to have an asymptote with 180 degrees angle. Okay? So the second asymptote is looking like this. And the third asymptote is going to be 120 degrees apart from this. These asymptotes would always be symmetric, actually. Okay? So here, the last asymptote would be looking like this. These are our asymptotes in this case. And these asymptotes would determine the behavior of the root locus when S goes to infinity. If S is very large, then some of the branches will match these asymptotes. Okay? Will be on top of those asymptotes. But for small k values, this is going to happen when k goes to infinity and when magnitude of S goes to infinity. So here we now start to see what we are going to have here. We see that this closed loop pole, it starts from the point -4 and it diverges away on this asymptote. Okay, it goes to infinity. And these two closed loop poles, they start from the open loop poles at -2 and -3. And they're going to approach each other for some small k values, and at some specific k value, where these poles are going to meet at a single point. Okay, and then they're going to go complex, and they're going to go towards the asymptotes at the end as k goes to infinity. Okay, so then this closed loop pole, it's going to start from here, and it's going to converge to this open loop 0 here. So here, when you see a root locus like this, you need to think about this like that. For each k value, we have 4 closed loop poles. The characteristic polynomial is this one, and for each k value between 0 and infinity, this polynomial has 4 roots. Okay? At k equals to 0, we have 4 roots of that polynomial exactly at these locations, -1, -2, -3, -4. Okay? As we increase the value of k, we have seen in the root locus that this pole is going to shift to the right for k is equal to epsilon, for example. And these two poles will come here and here, and this one will come here. Okay? As I increase k even further, then I will get this pole here, and these two poles will be here, and this two pole will be here. For some specific k value that we have, this pole is going to come here, and there will be two poles exactly on top of each other at this point in the real axis. This point does not have to be the point -2.5. Okay, so it can be something other than that. Okay, we know that it's going to be between -2 and -3, but we don't know its exact location. For some k value, there will be two closed loop poles exactly on top of each other in this interval. And for that k value, there will be a closed loop pole here. If we increase k even further, I see that this pole is really going to approach here, and these two are going to go complex now. Okay, so here I have these branches going there, and this pole is going to come here like this. Okay. If we increase k even further, these two closed loop poles are going to go away to the right half plane. Okay? Meaning that the closed loop system is going to start becoming unstable. okay, after some point. So we are going to be concentrating on these important points on the root locus. For example, if I know the k value at which there are two closed loop poles exactly on top of each other here, if I know the k value there, then I will know for which k values the closed loop system step response would be oscillatory or non-oscillatory. Okay? If k is smaller than the k value here, all closed loop poles are going to be real. Okay? If k is smaller than the k value at this location, then all closed loop poles, all four of them will be real. Meaning that the closed loop step response will not show any oscillations at all. But if I increase k above that value, there will be always two closed loop poles with non-zero imaginary parts. Meaning that in that case, the step response of the closed loop system will start showing oscillations. Okay? So similarly, for small k values, the closed loop system is actually stable. So all four closed loop poles are in the open left half plane. But for some large k values, two of the closed loop poles will go into the open right half plane, meaning that, they will become on the imaginary axis. Meaning that the closed loop system will become unstable in that cases. So we will be concentrating on locating these points on the root locus. Imaginary axis crossings, and these types of points are called breakaway points. We are going to try to locate those points and the corresponding k values as well. So here, let us now try to, for example, complete this root locus. Okay, so I haven't given some numbers here. So let me say that this is 2. Okay, this is the point 2. This is let us say that this real axis point is -1 and J2 here, minus J2 here, and let us say that this is minus 3. Okay. So far we only put the real axis parts of the root locus, and we put some arrows there. So the next thing that I have to do is to find the asymptotes. How many asymptotes do you expect in that root locus? What is n here? What is n? N is the number of open loop poles. Niğde open loop pole sayısı, Malatya open loop zero sayısı. What is n? For this example, what is n? 3. What is m? 1. That means that how many asymptotes do we have? 2 asymptotes. 2 asymptotes. Angle of the first asymptote is 180 divided by n minus m. Okay? Meaning that angle of the first asymptote is 90 degrees. Okay? And what is the angle between asymptotes? It is always going to be twice this number. Okay? Meaning that angle between is 180 degrees. Okay? And the intersection points of the asymptote is going to be summation of the open loop poles. Let me sum the open loop poles. So if I sum these two complex poles, what do I get? -2. And if I sum this, yes? -2 plus 2, it is going to make 0. Okay? And 0 minus the 0 summation, it is -3 divided by 2. And this is going to be 3/2. Okay? So here, the asymptotes are going to meet somewhere here, and the angle of the first asymptote will be 90 degrees. Okay? This is the 90 degree asymptote. And the next asymptote is going to be 180 degrees away from this. Okay? And if the first asymptote has 90 degrees, what is the angle of the second asymptote? Minus 90 degrees, or 270 degrees. Okay, so the second asymptote is going to be pointing there. And now, if I complete now this root locus, then I will just try to let these open loop poles. The branches are going to start from these, and they're going to go to these asymptotes. Each one of them is going to go to one of the asymptotes. Any questions here? Yes.
Does the arrow from 2 to -3 passing through an asymptote will create a problem?
So if you look at this system, what can you say about its stability? For small k values, there will be two closed loop poles close to these open loop poles, but there will be a third closed loop pole very close to this 2 point. Okay? So this actually means that for small k values, the closed loop system is unstable. What about for large k values? For large k values, okay, this closed loop pole is going to pass here. It's going to be somewhere. It's not going to be a problem for stability anymore. But for large k values, we see that these two closed loop poles would go into the right half plane, making the closed loop system unstable. So for small k values, the closed loop system unstable. For large k values, the closed loop system would be unstable. So if this system becomes stable at all, it's going to be somewhere in the middle. So which k values should I check in order to be able to find whether this system can be stable or not? I'm going to check. I can check at which k value does this system have a closed loop. This closed loop pole is somewhere here at s equals to 0, and I need to check at which k values these two closed loop poles would intersect the imaginary axis. Okay, depending on the k values there, I can determine a stability range. But sometimes it might be that for any positive k value, the closed loop system might be unstable. Okay, so it might be such a system. There might be such a system, and this might be one of them. So now let us try to look at the following scenario. So suppose that I have these closed loop, open loop poles, and let me say that there is a 0 here. Okay, so this is going to be a simple root locus. So let me say that this is -2, and this is -2, and this is +2. Okay. So now let us try to draw this root locus. I know how many branches will we have. How many branches do we have? 2 branches. I will draw 2 closed loop pole trajectories. Okay. In control, we will always be doing the same thing over and over. We are going to be given the open loop quantities. We are given the open loop poles and zeros. We are wondering about the closed loop quantities. We are wondering where the closed loop poles are when k changes from 0 to infinity. In the coming parts of the course, we will do the same in frequency response. We will know the frequency response of the open loop system, and we're going to be wondering something about the closed loop system again. In state space, we will be doing the same. We will have the open loop state space representation, and we will be wondering about the closed loop state space representation. So in root locus, we are getting the open loop poles and zeros. We are trying to draw the closed loop pole locations. And by looking at these figures, we can really say a lot of things about the performance and stability. For example, what can you say about the settling time of this system? Which closed loop pole determines the settling time of this system? So here, for small k values, the closed loop pole here for small k values determines the settling time. And as we increase k, what happens to the settling time? Settling time increases because the closest pole to the imaginary axis gets closer and closer to the imaginary axis. Settling time increases all the time as we increase k. For large k values, we see that these two closed loop poles might be determining the settling time after some time. Okay? But they're also approaching the imaginary axis, meaning that the settling time of the system is going to get always smaller and smaller as we increase k for this system. So increasing k will make the transient quite bad actually. So similarly, we can say sometimes which pole dominates the transient response. For example, we can determine the whether the closed loop system would show any oscillations in its step response or not by looking at the root locus. So here now, let us concentrate on this root locus. So let us fill in the real axis part. Do you think this part of the real axis is going to be filled? No, the total number is 0. What about this interval? It is going to be included here, okay? And what about this interval? The total number of poles and zeros, open loop poles and zeros to the right is 2. It is even, so this interval will not be included. And this interval will be included because the total number is 3. Okay? As soon as you place the real axis parts, place arrows, okay, so that you can see what is going to happen. So we see that here, arrows away from the open loop poles, arrows towards the open loop zeros. Okay? So I get this one. So now let us look at the asymptotes. When I look at the asymptotes, how many asymptotes do I expect? How many asymptotes do we expect? Niğde 2, Malatya 1. What is the number of asymptotes? 1. There is only one asymptote. What is the angle of the first asymptote? 180 divided by 1, 180. Okay? Angle between asymptotes. There is only one asymptote. Why do I care about the angle between asymptotes? Okay? So that means that these asymptotes, there is only one asymptote and its angle is going to be 180 degrees. Okay? That asymptote is going to be somewhere here and it's pointing in that direction, 180 degrees. Its starting point is really irrelevant. I don't care about its intersection point. So here I see that on the asymptotes there is going to be also a root locus branch diverging away on that asymptote. So now these two poles at k is equal to 0, we are going to start the root locus here, and then these two poles are going to approach each other, and at some k value we are going to get two closed loop poles exactly on top of each other. If I increase k further, what is going to happen? We expect them to become complex actually after that point. Okay? And now I'm going to draw a wrong root locus. I know that one of them is going to go to 0 and the other one is going to go to the asymptotes. This is as bad as it can be, okay? So you shouldn't draw anything like this. Why is that?
Because they are always complex conjugates.
Yes, here we are always considering polynomials with real coefficients, meaning that if we have complex closed loop poles for some k value, its complex conjugate should also be a closed loop pole. Meaning that root locus, when we draw it, it always has to be symmetric with respect to the real axis. If I have a complex pole anywhere, at the same k value, I need to have its complex conjugate as a closed loop pole. Meaning that a root locus can never behave, can never do anything like this. In this case, when I look at a complex pole at this k value, where is its complex conjugate? I don't find it. So this really doesn't make sense. So I really shouldn't draw anything like this. Then how should I complete this root locus so that at the end one of the closed loop poles should converge to this 0 and the other one should go to infinity to the asymptote? How should I finish this? These are actually going to jump to the other side indeed, that is correct, but the other one is going to be doing the same. Okay? So they're going to meet somewhere on the other side, and then for some k values the roots are going to travel here, and they're going to meet somewhere on top of each other at the other side. And then one of them is going to separate to the right, and the other one would go to the left, to the asymptote. Okay? So there is a classic question when we see a root locus in this manner. Usually in an interview, if you are getting an interview from control systems for the master's study, for example, in this department, there is a standard question that we ask when we see this root locus, and it is, when do you think, for which k value do we have the smallest settling time for such a system? which point should I concentrate on the root locus to look for the smallest settling time that we can have from this closed loop system? Yes. So here, the smallest settling time for this system is going to be obtained at this location when both of the closed loop poles are exactly on top of each other here at this intersection point. Why is that? Because here, as I increase k, settling for small k, what is the settling time? For small k, closed loop system is unstable, so settling time is infinite. And as I increase k, the closed loop system becomes stable, okay? And the settling time gets smaller and smaller, okay? And then when I reach this point, the poles, both of the poles are as far away from the imaginary axis as possible. As I increase k any further, one of the closed loop poles is going to start approaching the imaginary axis, going towards this zero. And that is going to make the settling time slightly larger. Okay? And that actually means that the minimum settling time is going to be reached when k is adjusted such that the closed loop system, both of the closed loop poles are exactly at that location. So as the final thing in this lecture, I would like to do something like this. Tell me an open loop pole location. Where should I place the open loop pole? Hadi ben burada diyeyim. Any other open loop pole? Do you want any more? Okay. Tell me zero places. Open loop zeros. Like this? Okay. So here this is our open loop pole and zero topology. So let us first try to draw the real axis part. Real axis will not be included here, but real axis will be included here, and it's going to continue getting included here at these locations. Okay? And then here, how many asymptotes do we expect? 3 asymptotes. Asymptotes are going to meet at some places. I don't know the exact location. Let me say that they are going to meet here. The angles will be 60 degrees, 180 degrees, and minus 60 degrees. Okay? These are my asymptotes. And then I know that some poles are going to go there. So these are going to go. I will let the closest poles to the asymptotes go to the asymptotes. Okay? And then what about these? What are they going to do? Do not look for anything fancy. It is just going to be this. Okay? So here in this case, that is how the root locus of this system would behave. What can you say about the stability of the system for positive k values? It is always unstable because of this pole and these two poles going in that direction. Okay? That's all for today. Thank you very much. Number of asymptote falan olabilir. Bilmiyorum. Hatırlamıyorum şimdi.
Hocam soldaki pollar neden direkt zero'ya konverge ediyor?
Efendim?
Soldaki iki pol neden direkt